My name is Beeman Strong. I'm the CPU architect for Intel Processor Trace. So we're going to talk about the feature and what we've added to Linux for it. I'm going to talk about the feature. Andy's going to talk about Linux. Okay, so this is a hardware trace capability, and it supports control flow trace today. So what that means is that we emit information about your software's execution. We do it in a way that we try to minimize the slowdown, and then your decoder software can collect that and can reproduce the precise flow of software execution. We target, as we list here, less than 5% performance overhead. The first generation is definitely higher than that, but upcoming generation will be right about there. In addition to this control flow information, we can also include timing information. So in addition to getting things like your branch targets and what have you, you can get CPU cycle counts to do kind of low-level IPC calculations, and you can get timestamp information so that you can align your trace with traces from other cores, other logical processors, or other types of trace, software trace, for instance. You have, I don't remember if I get into that here, but it can either be stored just to DRAM, or you can send it, depending on your product configuration, to like a debug port to collect it on JTAG, USB, or whatever available. Okay, components here. So obviously, you start with your Intel CPU that has the PT hardware. Then some Ring 0 agent software that can write MSRs will then configure and enable processor trace. Once enabled, that's the CPU is going to write out the PT packet log out to memory, or as we mentioned, to a debug port where it can be collected by a decoder. The decoder then is also going to collect some runtime information. So that's going to include basically some bookkeeping to allow it to make sense of what it's getting in the trace. So it's getting instruction pointers and the like in the trace log. So the information that it wants to collect so that it can make that useful is which modules are loaded and where, how do CR3 values, which are also included in the trace, map to applications, etc. Then it's also going to analyze or take a look at and disassemble the binary images, and this is because the data in the trace is purely dynamic information, and that's how we're able to compress it to the degree that we do so that we can minimize the slowdown. But then the implication is that all of the static information comes from the binary. So with that information collected then, the decoder can put all of that together and reconstruct the execution flow on an assembly level and pass that on to your PT-enabled tool to provide visualization, analysis, etc., and make all of this useful for you. Okay, a few more details about what's in the trace. So I just mentioned that the trace is dynamic information, so we emit as little information as we can. So for instance, for a conditional branch, we give one bit saying whether it was taken or not, because you can determine the source and destination from the disassembly. And so this gets our output bandwidth down pretty low to where we're under a bit per retired instruction. We see even like closer to half a bit. To be clear, that's still a lot of information, but it's a lot lower than we used to have a feature called. Well, we still have a feature called BPS that you may be familiar with. It's much higher. We also include some processor mode information. So this is mostly to help the decoder be able to keep track of software. So including information like CR3, which is sort of like our TIT indicator. Understanding when you're in 32 versus 64-bit mode, so the binaries can be disassembled properly. The MCS pointer, so we can keep track in virtualized environments of which guest you may be operating in, and the TSX transaction state. So if you're familiar with transactional synchronization, this gives you indication of when you're executing in a transaction, whether it is committed or aborted, etc. We also include periodic sync points within the trace, so this includes some CPU state. It's mostly just the state that's sort of relevant to the trace. It's not all, you can't get a register dump or something like that, but we include the current IP, the current timestamp value, the 32 or 64-bit mode, the current frequency, and the software context. So the idea is that at any one of these points, your decoder can skip to this sort of unique signature in the trace and begin decoding and have all of the information it needs to decode forward. And then finally, there's some hardware filtering capabilities. So In order to limit the size of your buffer or the total bandwidth, you can filter your trace by either CPL, so you can do ring 3 or ring 0, CR3 if you want to isolate an application, or you can specify ranges of IPs. So you can say, I only want to trace code that's executing in this function. A couple of other aspects to that. So there's some opt-in and opt-out filtering scenarios. So when you're being virtualized, the VMM can opt out of tracing if it wants to, say, allow tracing only within a certain guest or within guests in general. And then SMM and SGX code, those are both filtered out by default, though they can opt in if they want to be traced. Okay, here we go. Okay, so some usages, just to summarize a few, and I'm sure Andrew will talk about more. One, and definitely one of our primary debug uses is the ability to use this for post-mortem analysis, right? So you turn on trace, you let it run until you have your crash, your hang, your fault, your software anomaly of some sort, and then you've got this indication of exactly how you got there. And even a small, say, a 4K buffer would give you tens of thousands of instructions of path history, leading up to the failure. Or the event, I should say. Also, debugging user experience type short-lived performance issues. So sampling is a very common and very useful technique for performance analysis when you're looking at what's dominating your software execution, how is it behaving in its steady state, and produces a lot less data than something like processor trace does. But if you're looking at something that's maybe not statistically significant or doesn't last very long, using sampling at a high enough rate to look in these small timing windows is not very practical and comes with a lot of slowdown. Whereas processor trace, by virtue of giving you, information on a nearly basic block level and timing at a nearly basic block level, allows you to dig very deeply into where exactly your code executing slowly. Server cluster sampling. So, I've talked a little bit, a few times here about how, with trace like this and with this level of detail, we are producing a lot of information. So the prospect of having a server cluster with dozens of nodes and running this trace and trying to collect and process all of this information on all of them is rather impractical. But for purposes of being able to use processor trace to debug scenarios in this kind of environment, you can use sampling methods where you have a few nodes that are debug nodes, say, and once one of those is infected with whatever you're trying to debug, now you have the power of processor trace without kind of the full brunt of tracing all of them. Replacing your call stack with a full timed control flow trace. So the nice thing about this is with a call stack, you kind of just have from where you are back up to made on a function level, right? Where with processor trace, you have timing information included, and then you can, depending on how far back in your trace you want to go, you can see how you've ascended and descended within the call stack. So you're getting richer information, and even as you go through those functions, you're able to see, why did you choose this path first back? Because you're getting not just functions, you're getting all of the branches. And there are several others. You can use the information within processor trace to identify where you're getting unexpected weights from sleep states. You can certainly, it's obviously rather ideally suited for code coverage analysis. We talked about the TSX stuff, so you can look at, how often are you seeing aborts, how much instruction execution, or how many cycles are you losing when they occur. Okay, I'm going to let Andy now take over.
Thank you, Beeman. So I'm talking about the Linux implementation. I should add there are multiple Linux implementations. So this is just, I'm mostly talking about the perf implementation, so it has been integrated into perf events. And this is just an overview. I mean, you're probably roughly familiar with that. It's just how perf events work. So you have this abstraction layer which presents generic events in the kernel, and it presents it to different applications, both the perf tool or the other tools. Using it. And basically, we added the PT support and as a perf driver, so it's providing the data here. But there's one special thing, because normally perf provides everything in standardized events, so it's called a perf event. but we are having too much data because we would start decoding it here. Then there would be too many events and would be too slow down the kernel too much. But we instead we're providing the raw data to to the perf tool, to the raw PT data to the perf tool, in addition to some metadata, which has as the code, like the sideband data. And then the perf tool actually generates the perf events based on a PT decoder. So that's how we use it. Then the implementation, I already mentioned this. So it's integrated into perf events. It uses some metadata. For example, it needs to track context switches to know when you are switching to a different process. And then we have a user space decoder which disassembles the binaries. It uses Masami's instruction decoder for this, and then generates perf events, and then can do different analysis based on that. So the default analysis is actually doing a kind of sampling, because the problem is we're generating a lot of data, and perf hasn't really been designed for really extreme large amounts of data. So by default, we actually sample the data based on the virtual instruction time we are getting out of the PT stream. But of course, it can be also configured to give you everything if you're following some more slower. And as with perf, it's fully integrated in the OS, so you can actually use it as non-root, which can be a big advantage over other tools. It's context switch, so you can say, okay, enable it for some processes and not for others. So this is all, or you can also be filtered by T group, and yeah, it's available to non-root, like I mentioned. So the kernel driver, the basic PT kernel driver is in 4.1, the 4.1 kernel. The perf user tools, there's still some things we most likely will get into 4.3. There has been some more changes to that. So right now what works is you can run the perf user tools from a 4.3 tree or from our tree, and then run them on a 4.1 kernel. That works perfectly fine. And there are also some other users, for example, GDB and some others. So if you already have the 4.1 kernel, things work. Of course, in the future there will be some more enhancements, like there are some, for example, the support for IP ranges and some more filtering. But at least all the basic support 4.1. So PT modes. Currently what we have is what's called a Footrace mode. So basically you are generating data into memory, and then it's waking up the perf record process and writing it to disk. And basically it normally can trace continuously as long as the disk can keep up. But unfortunately, I mean, I should warn you that if you are running some workload which does a lot of execution, then usually your disk cannot keep up at some point because you have a lot of data. So, I mean, it typically works pretty well for shorter trace, and shorter means actually can be up to hundreds of seconds, depends on how much compute there is. But in most cases, I mean, you couldn't expect to do really long traces here, simply because there's too much data for you to save there. But at least in many cases, can do some work there. Then there's what we call a snapshot mode. This is actually pretty interesting. Is basically the idea is that you're running a trace, but you're not actually saving it to disk. You're just running it as a ring buffer in memory, and like recorder that Matthew mentioned earlier. And then you're waiting for some event. In this case, it's currently implemented by you just sending a signal to the perf process, and then it stops the tracing and just writes what's currently in the buffer. So this way you have much less data. You only get actually the path leading to your problem. But of course you still get like hundreds of thousands of instructions or branches leading to your event. So it's still a lot of information you can get. And then there's some upcoming features. We had them in some older kernel versions. Right now they are not yet in the kernel, but we expect them to be in the future kernel version. For example, one thing there was what's called sampling mode. So using normal sampling, for example, using a normal PMU profiling, and then but instead of you're also keeping a PT trace running in ring buffer mode, and then when you sample, you just grab some context out of the PT buffer. So basically, this way you can do things like you see some event, and you actually see how did you get to the event. So you can look at the exact path in the program to get there. That's really useful. So we could do this before. Intel has a feature called last branch records, where you can get up to 16, or now collectively up to 32 branches leading to there. But now with PT, you can get hundreds or even thousands of branches leading to an event. So it's basically, for example, if you have a problem like something is slow, but you don't really know why it's slow, so you need to know what's the the if statements and the conditional let there, but it's being slow, then it's kind of happy with that. Yeah. Another thing which should be coming soon is core dump mode. So with core dump mode, this is more for this what Bima mentioned earlier when you are interested really only when it's crashing. You not really care about performance, but you care about post-mortem analysis. So you can enable a core dump using a new R limit, and then the kernel allocates a PT buffer and keeps it running in ring buffer mode, but doesn't actually save it. And only when you're crashing, then it's writing it to disk, and then you can use a debugger to analyze it and then actually see how did you crash. Yeah? This is also should be really useful. And then there's also what you're looking at. There's some system crash mode. So this is basically the same thing for the system. So you're running a global trace, and when you're panicking or hanging for some reason, then you can reconstruct it from your crash dump or also from P-store potentially. So this is a similar approach like what Matthew talked about earlier for LTTNG, but instead of using software tracing, you can use the hardware tracing. So these are the PT modes. Here's an example, for example, DDB. So DDB 7.10, this is an upcoming release. It should be out soon, I believe. So it supports PT now. So you can do things like backwards debugging or reverse step. So if you enable the PT trace and then you stop at a breakpoint or on a crash or something like this, then you can actually see how did I get here. In this case, I'm only showing you the instructions, so it can reconstruct instructions. You can step backwards, so you cannot actually see any data because it doesn't record data, only records branches, but at least you can see how did I get there. So you can exactly see what's happening. I only have one example here, but there also you can do things like all the function calls that led to my crash, or you can also display the source code lines, of course. In this case, it's only an instruction, so it's pretty flexible. So this basically makes your task of figuring out where did you crash easier. Yeah? And of course, you can also browse the trace. So if you, for example, you're just interested what's going on, you can jump forwards and backwards in the trace, and there are different options to do this. Here's an example. Okay, this is Brandon's flame graph. So because we are just generating standard perf events, so we can basically just generate a standard histogram based on our PT trace. So this is a similar output as you would get if you're just doing standard sampling and then feeding it into Brandon's flame graph tools. But in this case, it's actually using a much higher sampling frequency because it's with PT we have all the branches, so all the complete context. So we can do virtual sampling just at decoding time, and we can give you much more information. We could also, I mean, this is currently not implemented, but it could be implemented with these tools, is because we actually know, for example, for each of these different colored boxes, how long they could take, yeah? Because we can reconstruct this information from the trace. We know exactly, for each function, we can sum up exactly how many cycles did it take. So we could, for example, annotate this here and saying, when you click on it, you see, okay, this took that many cycles, that many percent of your cycles. So there are some experiments and going into this direction. Currently, it's not implemented with the standard flame graph tools. Yeah. Then another thing, and it's somewhat experimental, but it's already in the perf tree now, is so the idea was we can generate a lot of data with PT, but how do you analyze it? So there's actually a script now which is built on top, a Python script which is built on top of perf script, and it can write the complete PT data into a database. I think the current implementation uses Postgres, so you can write all information Postgres, and then you can actually use SQL queries to see what you want to do with the data. So this is an option if you want to do custom data analysis and see. For example, we have an example in the tree which just generates a call graph and a histogram, and it just tells statistics how many cycles every function took. So this is one example analysis. But of course, you can do everything. Everything you want the script for, you could use it, and then using just standard SQL tools and so on, and even standard data mining tools to be used on top of that. So this is,
yeah. Is that possible to use any SQL database?
Yeah, I think in principle, yes. I believe there's one or two Postgres in the script right now, but it should be easy to fix. So it's actually on my list because I wanted to just put it into SQLite. That's much easier than Postgres. But right now it needs some small changes, but it's not nothing big. Yeah. So the reason I think he's currently using because it's a lot of data. Yeah. So right now it's using a Postgres specific bulk data import option, and it deserves just to be ported to another database, then it should be possible to use something else, whatever you like here.
Quick question. Have you thought about, because do you run often into situations where the database has a problem coping with the amount of data that is kind of being generated out of your traces?
We haven't really seen much problems with that. So, I mean, most of the problems with too much data was on the perf tools itself. So we had cases where especially the coder ran really long, and there were some optimizations to make the decoder run faster. I have high hopes that there's a patch kit being worked on right now by Namjoon to multi-thread perf analysis, so it can run multiple threads. So that should be a lot faster, because right now everything is single-threaded, unfortunately. But in the database, I hadn't had a lot of problems so far. But I mean, I don't think we did really large analysis on the database. But I mean, this is more, somewhat experimental stuff.
Yeah, because for larger files, running analysis on top of that, I mean, you might want to consider kind of doing that on the spot, using basically the trace as your data storage, and basically do kind of a sequential search within this wrap. I mean, for some types of queries, that should be you should be able to stay much more compact by using your trace representation rather than exploding it into the database.
Oh yeah, I mean, there are different options, of course. You can have custom tools, and there are actually some custom tools which are doing this. For example, VTune is a commercial entry tracing product, or profiling product has a custom database for these kinds of things, and there are some other experiments. But the idea here was more that allows everybody who's maybe familiar with data mining in the database to play around with it. So I mean, if you have really then a production use of this, you might be possible to do something more efficient. But at least for prototyping, I think it's a great option. Yeah. But it's actually not that slow. At least once you have the data in there, the database does a reasonably well job. And again, I mean, the really interesting part here is, again, with PT is, so we can generate a lot of data. We can tell you a lot of things. We can trace everything in your workload. Yeah. So the problem here is really not anymore how to get the data, but what to do with all the data you have. Yeah. This is as the tracing becomes better, that becomes more and more the issue. So what to do with all your data. Yeah. And of course, the really interesting part is to do custom analysis on top of it. Yeah, for example, some of the things that Matthew mentioned earlier, for example, really standard analysis, which I often use personally, is just always measuring the latencies between two events. Yeah, for example, or even a single event, like you have one thing happening, just care about how often it happens and what are the distributions of the intervals. But in other cases, for example, you have something like open and close, so you care about what are the intervals between those, and do some statistical analysis. So a simple way to do perf script, to look at perf script output and do some analysis. That's actually what some of my tools do. Another way is, if you want to go more level, there's a library called libipt, which is on GitHub, which allows decoding processor trace on your own. So you could write an own tool, a low-level tool, which directly reads the trace data and does fast analysis based on that. So it would be very low level, but it would be more work because you have to provide much more infrastructure to do this. Then you could also, of course, go even more low level and do it on top of the kernel interface. I'm not sure I necessarily recommend that, but it would definitely be possible. And then also you could do it as a backend of the SQL database representation.
Would you be interested to eventually create a bubble trace plugin to consume a IPT an Intel trace?
So actually, I haven't tested it, but in theory, I mean, it should already work using the CTF interpreter. The CTF output in perf. So if you could generate CTF out of PT, and in principle, it would be also possible to be able to plug in. Right now, there's no plans to do this, but I think it would already work with the CTF output. So in theory, you could load it into Trace Compass. But I mean, I actually tried it once. To put it in there using a different conversion. The problem right now with really generic tools like this is because the really nice thing about analyzing PT is when you do it in a generic tool is if you somehow map it to the source code. Because we have all this control flow data and then we have source code and we somehow want to see the relations between those. And right now tools like Trace Compass, they don't really have this mapping to the source code as far as I can tell. Or maybe I'm wrong on this. But
well, this is actually This is one of the extensions we
Yeah.
plan to do in CTF 2.0 is to
Okay.
allow expressing mappings of with the source code and everything.
Yeah, but in generally, I mean, there are lots of interesting ways to use this. So I think the really interesting part is, if you're interested in using processor traces, so you have all this data, what can you use of it? Yeah, can you make use of it? Can you have some nice tools for just solving your problem? Or so that's, I think that's a really interesting part. Okay, so there's some more tools. So I mostly talked about perf so far. There's also Intel has some closed source tools. There's something called Intel System Studio, the debugger, which can then access the debug port, for example. And there's also VTune. VTune has support for some things on processor trace. So this is a commercial provider. And it has much fancier GUI than perf. So it guides you more, but yeah. Then there are some third-party debuggers, hardware debuggers, which can use processor trace. Like there's Asset Intertech source point for Intel. Okay, it's Arium. Okay, it's Arium. And then there's also the Lauterbach tool, which can also use this. So these is typically, so you need a special trace device connected to your system and get the data out this way. There's also SimplePT. This is my own project. This is a really simple decoder, and it's not integrated in the kernel. It's a loadable kernel module which just programs the PT hardware, and then it uses libipt to generate data. That's really new. I just announced it like a week ago. So this is it's standalone. It's easier to experiment with. I use it for some experiments, and it should be more simple to port to other environments, so like older kernels and things like this. And then we also have the libipt decoder. This is a standard decoder which you feed in PT data, and then it spits out instructions or branches. So this is a building block for other tools. And there's also Intel has something called the Intel PAL Platform Analysis Library, which is like a collection of different libraries which can also get both processor trace and some other tracing facilities. It's also available on the Intel website. So summary is, the processor trace is already available. In fact, I already have it on my laptop, so I don't have time really for a demo now. But if you're interested, I can show it on my laptop. So it's available on Intel Core CPUs, starting with 5th generation, so Broadwell, Skylake, and also some others. It's integrated in Linux perf 4.1 for the kernel, and will be hopefully in 4.3 for the user tools, and it will be as in the upcoming GDB 7.10, and provides rich data on program execution. And there's also some references. For example, I wrote an article on the perf implementation on LWN that has some more examples than I have here. And there's the libipt processor trace decoding library, and the GDB is supported available. And there's also, you can get SimplePT if you want. It's on GitHub. Okay, I'm open for questions.
Okay, well, first of all, this is a very welcome feature.
Thank you.
I mean, a lot of other processors have that for a while, and it's really good that Intel can provide that now. Few questions. The core dump, you've mentioned that you wanted to integrate that with the core dump in the future. There was a core dump, a mini core dump done by Linutronics this year. So this is also part of the diagnostic and monitoring work group. So it's done in a way that all the information that you don't have to put in the core dump, you don't put it. You can calculate it after the fact, post-mortem. And one nice thing about many other processors is that you can also put in there what they are recording. You know, where you are in your code exactly, which branches and everything. So you can put that into that mini core dump. So hopefully this can also be done with Intel here. So if you can also look into that mini core dump when you're in there, that would be quite useful.
Yeah, so I haven't looked at mini core dump. Is it like a kernel feature, or is it user space?
It's a user space.
Okay. Yeah, in principle it could be done there, because we have the kernel interface, so there's perf. You can use the perf event call, and you can do self-tracing, and you just get the PT data in your memory. So it would be possible to implement this. there's yeah, you would need to do some extra information for the sideband, but yeah, it would be definitely possible to implement this. I don't think we have looked at it. Yeah, but it would be possible without changing the kernel.
Other questions related to GDB. Is it the same overhead? Like you mentioned in the slide somewhere, it's about 5% or around that. So when you do the reverse debugging, it's the same type of overhead, or it's bigger. Or?
I mean, when you reverse debugging, you already stopped it. So the debugger is running and it does it very fast.
But to be able to record all the information so that you can go back and forward or
actually, I don't think we measured long-term traces. So the basic CPU overhead from PT is the same, like 5% or can be more on Broadwell, but about 5%. I think GDB does some extra instrumentation. It might stop on some twist calls, so you might have a little bit extra overhead simply from running GDB. But I don't know how much it is, but it shouldn't be a lot.
So because this was an issue with the implementation in GDB. It's because in many implementation for the reversible debugging, it was adding way too much.
Oh no, it's billion times faster than the old stuff, because they have the reverse debugging in there, but it's actually stopping every instruction and recording all its input and output. This is not doing this because the hardware is doing it all for us. So the overhead is many orders of magnitude less.
Okay, fantastic. And which type of processor is supporting that for GDB?
So for currently shipping is Broadwell CPUs and then Skylake and there will
Okay. And any discussions with your Wind River folks to get this also into their system viewer, or because you've mentioned many of the system viewing tools from Intel. But Wind River, I mean, do you have the Trace Compass stuff?
We have talked to them about it. They're aware of it. I don't know if they have plans for it right now. I'm not sure, if their market with Intel is enough to warrant it. That's been my impression. I don't know for certain. Let me just add one other thing about the performance overhead there. That 5% number is sort of purely the hardware. So how much your software slows down just by virtue of logging. Additional software overhead with your, collecting sideband or storing stuff out to disk or whatever is not accounted for there.
And it does an average number. So you might have some workloads which are slower, and especially in Broadwell some slower. But I mean, this is averaging out. It basically depends how well it compresses. Yeah. So that's normal.
I don't want to take the whole question period. So any other question? Yeah.
Hi. Thank you. It's a good presentation. So I agree with you about the amount of data. It's like so much that it overwhelms you. Is there any approach to actually sanitizing the data, which is uninteresting? Can it go filtered so that you could actually look at something which looks like an anomaly in the entire trace, which is actually very helpful in saving time, because usually if it's like a multi-node system, so like electron traces are not then, and they all make sense together.
So we have multiple approaches here. I mean, one approach, of course, you can do filtering in advance. There's some ways to do this. So start and stop, like classic, you can do triggers. But like if you look at my the different modes I have here, especially the snapshot mode is basically for anomaly, because you just keep running, but you don't actually save the data. It's just in memory, but it just most of the data is overwritten again, and you only save the trace when actually something happens, and you define based on a trigger, but when you save the trace. So this is exactly defined for this case. The other case, which also can minimize the data quite a bit, is sampling mode. So you're just getting it around specific events which you're sampling. And also in the core dump mode or in the system crash mode, it's the same thing. You only saving the data when you're actually crashing, because you care more what happened in the last 100 milliseconds before my crash, but you don't care about anything else. So there are already multiple of these modes are exactly designed to minimize the data, that you only get the data around your event.
Okay, you've written event. Is it event or events with multiple events?
Sorry, say again.
Like you can. Are you can you say on multiple different events of interest? It's a single one or it's multiple?
So the way snapshot mode is currently defined as you're sending a signal actually to the perf process. So you can send as many signals as you want. For sampling, it's just based on time. So it's arbitrary, just based on time. The core dump and system crash is just whenever you're crashing, because typically it's a fatal event, so you're not continuing after that. So perf currently doesn't support it, but actually in SimplePT, that's my experimental own implementation, it has supports multiple triggers. So it can define cape probe and start a trace on a cape probe and stop the trace on a cape probe. So there are the capabilities to do this there. So if you want it there, so basically, but this is currently not implemented in perf. It's only in the experimental implementation.
Yes.
Is there any integration in these tools with the processor's other performance counters? Like sometimes I'm debugging a performance issue and I can tie it to an increase in L2 to mem cache misses or something like that. Currently, the tools to extract that information from the MSRs are kind of painful.
So I mean, so directly the hardware cannot directly trace it into the PT buffer at this point at least. If you do, for example, use the sampling mode here, then you're using sampling on some performance counter. So you could do, for example, say I'm sampling on L2 misses, and then every time I have an L2 miss, I collect a little bit of PT trace out of my buffer. So this is the idea behind sampling mode. The other thing, of course, is sometimes you can also look at just the timing. For example, I mean, it can be not. Some people do this. They just look at it because if we have cycle accurate trace, we can see, okay, this most likely there was a bad cache miss here because the load took really long. But again, we cannot go down to a single basic block. We typically have multiple basic blocks to the way the tracing works, so it might not be accurate enough. So the best thing is usually combine a different trace. And the other thing, of course, you can also do, you can run a software sampling of, for example, the MSR states, and then combine it based on the timestamps. So this is the other approach, so that you synchronize it with other things. So people have been doing this also with other events. For example, one thing that Bevan mentioned earlier, there was a really nice demo. That was to synchronize it to a video of an application. And every time there was a latency, you could actually, based on the frame, you could find it in the trace. Yeah, so there's some really cool things you could do. But these are currently a little bit beyond perf. This is some of these usages where you might have to have your custom tools to do this. Any more questions?
So with what is present today, can you basically map a file system with PMEM and DAX and then point the PT buffer to persistent, basically either non-volatile memory or eventually RAM that can be kept across a reboot or with kexec? Is it possible to do that today?
Yeah, this is the system crash mode. It's upcoming. So we had done prototype, but so there were actually two. We actually didn't plan currently to directly write it to PMEM. So the idea was because most crashes you can actually still execute some code. So we had something what we called the flight recorder. The idea was to in the driver once have a panic handler and then write it to a pstore file which works today. In principle, this could be also extended to PMEM, yeah. But the other approach is, so this was more aimed for client systems, because on client systems, we typically don't have a full crash dump, because the way Linux crash dump works is you need a kexec kernel, it needs quite a bit of memory to reallocate, so that's a little bit too much for a small system. So on larger systems like servers, where you're using a kexec-based crash dump, so you execute another kernel and it does the dumping. And in this case, you can't just extract it out of the kernel image. And we've been looking at that. Actually, it was not done by us, but I believe there's somebody from Fujitsu who's looking at this currently, so extending the crash tool. And then so you just enable the trace and you lock it to memory. And then once you're dumping and you're looking at the crash tool, you just find the buffer in there and then you decode it.
Because I work with customers who have tight constraints on the time it takes to reboot their system, but they also want to gather the traces that led to the crash. So the idea there, I mean, using PMEM and DAX for this kind of use case, if the BIOS does not reset the memory, would be ideal. Unfortunately, on Intel, there's no guarantee about that, but it allows you to reboot back into your fully up and running system and then extract your trace buffers. So, I mean, I'm just giving you a heads up. This is really a requirement that we had from customers.
Yeah, I mean, it wouldn't be probably not very difficult to implement. Just have to add a little bit of code to the kernel driver, so I wouldn't expect it to be that difficult.
So does your PT buffer needs to be a linear, contiguous linear mapping?
So it depends on. Okay, those are some of the details we left out. On Broadwell, it has to be a single buffer and has to be continuous. We're actually using a software scheme to multiplex it. So we are doing an interrupt and then we are switching to a new buffer. On Skylake, the hardware is very flexible. You can specify as many buffers as you want. It's better for performance if you use larger buffers, then there's less overhead. But you can use multiple, and it's actually in physical addresses. So you specify physical addresses, so it's no problems like with tabs. So it's pretty flexible scheme.
Other questions? Okay, well, thank you very much.
Thank you.